Hello again, and welcome back to Information Storage and Retrieval. Today we're going to get into the basics of how Boolean retrieval works. This is our first step toward building a search system for, uh, you know, unstructured information, right? So first, let's touch back on why aren't we just doing human search? Human search is linear, right? If you have a pile of things, you just have to go through them one at a time and then make all these decisions about, okay, is this book likely related to the thing I'm trying to find or not? There's no intermediary here. It's just you and a collection of documents. That'll be important. Documents, our definition throughout this course is a document is anything that you might want to search through or for. Mostly we talk about this in terms of text, and that's all that we'll be focusing on in our programming sessions. But it can also include anything, videos and images. Our term for document is very broad in this course, so keep that in mind. So human search is not great, right? We don't want to have to hand sort through everything that we have. Imagine trying to use the internet if you had to manually look up every page to figure out if it was related to the thing. You probably don't even know how to do that. It barely makes sense as a thought, right? We're so used to using something like Google. But the question is, okay, fine. If we have all started to employ Google for this task, lease out our lookup to them, how do they do it? So the first step forward in trying to get access to information from the big broad world is Boolean search, also sometimes referred to as filtering. So Boolean search is this method of narrowing down all of our possible choices using Boolean operations. So we can use these logical operations to decide which documents in the world, in our collection of documents, do or do not relate to our information need, right? So let's talk about how this works. How do we get away from just straight up linear search? First, we'll start with a discussion of a sort of a proto. I mentioned the indexing process as very key. This is sort of a pre-index. The ideas that came about before indexing was more of the go-to method. That will help us talk about some Boolean operations and how to do search with those operations using this incidence matrix concept. And then some of the limitations of why we don't use these incidence matrices. So, how do we get away from linear search? As I mentioned, the simplest, most brute force way to search is just linear. We'll do a little example here. Search for the word needle. I found it. Have you? It's in the sort of the middle on the far right, right? That takes you a little bit of time. There's no organization to this information here on the page. You had to find needle. Didn't take you too long, but let's talk about why, how that scales up. So, linear search will work, but doing it in a larger setting is not going to be efficient. So once again, search for the word needle. Oh dear God. I honestly don't remember where it is, and I'm not going to find it here on this slide. That just shows, that eventually we very quickly outstrip our ability to brute search things. Now, even if your computer is extremely fast, if every time you had to look something up, you had to search through the document, linearly, and you had to do it over 10 billion documents, even the fastest computer in the world is going to be it's not going to be very efficient, right? So now this doesn't mean that linear search isn't part of the whole process that we're going to go through here, but the idea is we need to minimize the amount of linear searching that we do, and maybe we only do it once so that we can build structures to help us much more quickly search. So, along those lines, one of the simplest processes for linear search that a computer can do is called grep. You may have heard of this. Grep is short for Global Regular Expression Print. A lot of command line tools have this built in right by default. It's basic. All this does is a linear scan front to back, and it finds the exact substring of text that you're looking for from a larger string of text characters. So let's look at a grep process. So is the word name in this string? So the grep string and substring. Using your human brain is cheating here. We're gonna walk through the process of grep. So how does grep do this? Well, the substring is using your name is cheating. The substring is name, and we're going to count the steps that it takes. We'll just move this substring along ostensibly. We move the pointer at each step of the string and say, hey, how many is this a match, right? So first, no. I, comma, am, no, that's not right. Comma, my, no. Aha! We have found the word name. Grep can come back and say, yeah, it's in there. I found it. So how long on average can we expect this to take? This is the key question, and this is why we get away from grep. So this concept of runtime it's very big in all of computing. Anytime you're looking at the way an algorithm executes, how long it takes to do it based on its inputs, we talk about runtime because a more efficient algorithm is always better. And sometimes that difference is not just like, oh, it's quite nice to have a faster runtime. Sometimes that is the difference between something that is useful and something that is completely useless, right? So let's look at grep's runtime. From the beginning to the end of a document, scanning one document of length n, number of things in it, right? Your substring, the thing that you are looking for, it could be anywhere in the document. We don't know, right? But at the start, when we're starting to search through a document, we're not sure if the word is there or not. So if the word's at the beginning of the document, hey, it takes one step. We got it in one. Great. Easy. But if it's at the end of the document, it takes n steps. It's going to take you the full length of the document to hit the word and say, oh, shoot, there it is, right? On average, that means, based on the fact that this word could appear anywhere in the document at random, that's going to be n over 2 steps for any given document. And even worse, if the thing doesn't happen to be in the document at all, it will always take a full n steps to determine that. Yuck. So, look, this is fine, actually. A linear runtime is okay. But if we're doing linear runtime over 10 billion things, that's not great. So let's look at if we're trying to grep an entire collection. N over 2 steps on average per document. If we have 10 documents, each one's 100 words long, 100 steps long. Well, okay, that's fine. That's only 500 steps. A computer can do that pretty easily. Might take our eyes a little bit longer, but that's fine. But then if I'm doing 10 million documents, and each document is 100,000 words, that's 50 billion steps on average. And that's every time you want to look for one word, right? Now, that's reasonable when we look at this from the stance of a human. Like, yeah, it would take me a long time to search the Library of Congress for a single word, of course. But we're trying to do a lot better than that. We're trying to build a very useful search system, comparatively. So, again, we'll talk about runtime pretty regularly, and it's a really important idea to just have down. So it's a very large idea in programming. You're not going to need to, you won't do a runtime analysis yourself, really, but it's something that is useful to have in the holster. So we use what's called big O notation to talk about runtime and how an algorithm scales up. So big O is how to represent that. Big O of C, for example, is constant time. This is the best possible thing. The operation will always take the same amount of steps, regardless of how large the data is. A way of thinking about this is arrays. Arrays in computing, right? You don't need to search through an array to find one of its elements. You just give it the index and it pulls it straight out. There's no looking at each one to make sure we've got it. We just know the address. Versus linear time. Now, this is fairly average for most algorithms. This is the number of steps it takes will scale at the same rate as the size of the data. So, I poo-pooed grep's runtime, but it's fine, right? This is what you can sort of expect out of any given algorithm. Grep's runtime is big O of n. It will scale with the size of n. We also, just to note, that big O doesn't care about halves or 2 times or 3 times, because it's much more concerned about how much this thing will scale up. Like, is it going to go up exponentially, right? Or is it going to go up linearly? Or is it going to go up not at all? Is it a constant operation? So some operations scale pretty dang well. Log n, for example, is one runtime that is quite nice. Logarithmic time. Now, I'm not going to require a bunch of math, but remember, logs go up quite slowly, even as the length of the thing goes up quite a lot. So the data has to increase by an entire order of magnitude, like 10 to 100 or 100 to 1,000, for it to more or less double the runtime of your operation. Like I said, running on 10 times the data will only take twice the time. That's why any algorithm that has a log n runtime is really good. On the other hand, some operations scale extremely poorly. For example, quadratic runtime, that's not great. Every time your operation will take the squared runtime of the length of the data input, or even worse, exponential time. This is the inverse of log. The runtime will double every time you add an item to the data. This is awful. You don't want this kind of operation, because it's just not scalable. And we'll touch on examples of these, but the big idea is big O notation helps us quickly capture how well something will scale to a very large setup. So, we'll talk about these more in depth, in concept, as they come up, if that's even necessary. But most of what we're doing here is designed at connecting these algorithms and facilitating search, and just knowing what the big O notation is, and sort of which are the good ones and which are the bad ones, is sufficient for understanding how we use big O here. And hopefully we'll get you a sort of intuition for what big O is about if you ever come across it again. So, grep, we don't want to use this to search the Library of Congress, right? We don't want to use grep to search the internet. That's not viable. But it's still part of what we do. It's still part of all of our processing. We still have to linearly search through a document to build something useful in terms of a retrieval structure. So this is good. I mean, it's a great tool. Computers are actually pretty dang good at it, and they just blitz right through text like that. But we only want to really do it once. So that's where we step into the realm of building some kind of retrieval structure. So let's talk about term document incidence matrices. Indexing in general is the idea that we're going to front load all of this work, all of this brute force work, all this search work into some kind of structure that will help us make sense of the documents, as opposed to just trying to do that same brute search every time we need something. Terms, this is the basic unit of search. This is usually just, the easiest way to think of it is words. So the words of a document are its terms. Now we need to do a little processing to make words into consistent terms, but we start here with this idea. Document is whatever thing we're searching through, and the term document incidence matrix has, for the rows are the terms and the columns are the document names. So in each cell of the matrix, there's a 1 if the term is present in that document and a 0 if not. So for example, document 1 has terms B and C, document 2 only has C, and document 3 has A, B, and D. Right? So how you build this is basically scan through the text and record where words appear. So how do we step into this world of doing this to, say, a big old pile of textbooks or academic documents or song lyrics or whatever, right? First, we have to define what are the terms. A lot can go into this. The terms are words that have been normalized. So normalization is a key process here because it makes it so that we don't get hung up on small superficial differences between the text. Things like the way punctuation is used, capitalization, all that kind of stuff. So now, we do sometimes make exceptions when we're building a system like this. We might need phrases or proper names to go into their own terms, as opposed to just chunking them down into very similar term ideas. So let's run through this process. Document 1, I have a cat. Document 2, her name is Little Bit. Document 3, she is not a graceful cat. Document 4, but she is sweet. So, how do we build this out? First, the first idea is we're going to have to build our terms, right? Our list of terms. Here's our documents and our terms. And we can run through each document and record the terms that occur. So, I, normalize down. That happens in document 1. Have, cool. A, great. Cat, cool. Document 2, her name is Little Bit. 3, she is not graceful, or not a graceful cat. Okay, finally we're starting to see some overlap, right? We see that documents 1 and 3 have a and cat, and then documents 2 and 3 have is. These are the shared terms between the documents. Finally, 4, but she is sweet. Okay. This is our term document incidence matrix. We'll talk about how to use this shortly, but we'll work another example. Here's the Dr. Seuss, some lines as our documents from Dr. Seuss, right? Would you like green eggs and ham? This narrator is really pushing this egg situation on Sam I Am. Kind of a little bit rude, if you ask me. But here's our terms in this set of documents. And we can go and record where they occur, right? Document 1, document 2, document 3, document 4, document 5, document 6. Okay, so how we did this was a linear search. We went through each document, and once we pulled out, okay, is this word present or not? Great. We're getting very close to the key concept of what information retrieval is all about. Because we've taken documents and turned them into this intermediary lookup structure that we can now use to filter down our set of documents. So we do all this linear searching up front, and now we can search the matrix instead of the raw text. We can use Boolean operations to find out where does a particular word live in this collection of documents. So, Boolean operations and retrieval. So using Boolean operations, we can now select documents, filter documents, based on the search terms that we've built into our term document incidence matrix. So let's recap a little bit about Boolean values and operations. So remember, this is useful. You've probably encountered this before if you've had some programming, of course, but we need to recap it a little bit, get it fresh. So Boolean values. Boolean values are also known as bits, and they are true or false, 1 or 0, yes or no, the full basis for modern digital computing. Digit being binary bit, right? Tens, but yeah. So the way we operate on Boolean values is using these Boolean logical operators, and, or, and not, right? These are the basic ones. There are others, of course, but these are the simple ones, and we're mostly going to focus on and here. So, and is true only if both A and B, the Boolean values, are true. Otherwise, it's false, right? I need both of these to satisfy the conditions. Whereas or is either A or B can be true to satisfy my conditions. And not is just invert whatever my current condition is. So if I'm true, turn it false. If it's false, turn it true. Now, how do we use this with the term document incidence matrix? Boolean strings. These might be familiar. So you can just do this on a large string of information, 1 bit at a time. So let's work a couple of these out, just a little bit at a time. Haha. So let's say we have these two Boolean strings, 110011 and 101101. We'll use the same ones across the board. Let's do an and to this. So, and the first column, okay, 1 and 1. Yep, that works. 1 and 0, no. 0 and 1, no. 0 and 1, no. 1 and 0, no. 1 and 1, yes. Great. Okay, so now we'll do or. You'll see that or is much more permissive here. 1 or 1, great. 1 or 0, great. 0 or 1, 0 or 1, 1 or 0, 1 or 1, great. All of these specific pairings satisfy our conditions for or. And then just finally not, we'll invert it. So not 1, that's 0. Not 0, that's 1. Not 1, not 1, not 0, not 1. Right? So this is the basis for how we can use the term document incidence matrix to dig into our collection and find things that match a particular query. So this brings us to Boolean queries. So a Boolean query is a logical expression that uses terms, so words that we're interested in finding relevant documents for, and Boolean operations, like we just covered, to select a set of documents. So word 1 and word 2 finds any documents that will contain both of those words, whereas word 1 or word 2 finds any documents that contain either of those words. So the term document incidence matrix that we built before, that's just rows of Boolean strings. Hey, we know how to do this now. We know how to execute a Boolean operation to retrieve some documents. Cool. So let's look at my cat documents again. Here's the matrix. So here's a query. I want all the documents that contain cat and graceful. So let's pull out the string for cat, the bit string for cat. Okay, 1010. So that means documents 1, not 2, 3, and not 4 contain cat and graceful. So that's documents, just document 3, right? Now with our human eyes, we already know the answer to this, but we can do this algorithmically. So run through our operation and these two strings together, and you just get the third item of the string is true. That means document 3. So if I'm looking for cat and graceful in this little set, then I achieve document 3 as my result. And that makes sense because that's the only one that has both of those words in it. Let's do it on the Dr. Seuss version. So, same situation. We've already built our term document incidence matrix. And we want to do a couple of search queries, right? Query 1, not and like. You can already tell there's a lot of them there. We don't know exactly which ones do and do not have both of those words in it. And so this is where it gets useful to figure out how these documents line up in terms of what terms they contain. So, not, great. That's 0 and 1, 0 and 1. Like, oh, well, that's every document here. So every document contains the word like. That's how Dr. Seuss works. So let's do it. Let's and it out. I can shortcut it to you. It's going to be the same as not, since the like one doesn't really add much. So that means the query for not and like turns up documents 2, 3, 5, and 6. Great. Let's do or. Here or anywhere. Now, or is an actual term as well, so we're talking about the logical or in this example. So we'll pull out the one for here. We'll pull out the one for anywhere. So any document that contains here or anywhere, so anything that's pertaining to space, right? We can run the operation again. So 0 or 0, no. 1 or 0 or 1, yes. So the back 3 documents, 4, 5, and 6, would satisfy this search condition. Now let's do not. So I want only the documents where we're not being negative, right? So all the documents that contain not, that's 2, 3, 5, and 6, we will not that. So that becomes 1 and 4. So this search returns documents 1 and 4. Those are the only ones that do not contain the word not. So this gets us into the world of even more complex Boolean operations. We can ask more complex questions. So you might need to ask, I want one word and either of a set of other words. Or even worse, I can say not one of those words, right? So I want either word 1 or 2 and I need word 3. So the idea is we can sort of expand one of our basic terms into something, expand our search a little bit by using or, but still narrow it down properly by using and. So a quick note on the order of these operations. Typically, if you write these out in plain text without using parentheses, not is so like PEMDAS, right? Please excuse my dear Aunt Sally, all that stuff. The order for Boolean operations is typically not, and then or. But this is ambiguous, so we will, for our purposes, we will always use parentheses to make sure it's very clear what we're doing. So let's go back to our cat matrix. This is the query, I want any document that has she and is, as well as those they also cannot contain the word graceful, is what this boils down to. So she and is, and not graceful. So she and is, we'll do those first, right? We just do them each one at a time. So she and is, okay, that gives us the string 0011. This is our intermediate result, okay? Now we can jump over and satisfy not graceful. So what's the graceful one? 0010. So graceful only occurs in document 3, right? So now we will not that and say, okay, so any document that does not have that word graceful, that's what we're going to pull out here. Great. So we have another intermediate result is 1101. So we have these sort of intermittent steps to get us to this final bigger operation. So 0011 and 1101 brings us to just document 4 satisfies these conditions. So you see, we've gone through a little bit more complex process, a more complex information need and search. So document 4 is what we pull out of here. We'll do this again on the Seuss documents. So I want you or Sam I am and not them. I don't want any documents that contain the word them, but I'm okay with documents that contain the word you or Sam I am. So you, that's 100100. Sam I am is just in that second document, so we'll combine these with an or, right? That expands our list of viable answers. We also need to take the not of them, so we'll take them and not it out, so only the documents that don't contain them. Result 1 is that union of you and Sam I am, and result 2 is the not of them. The only document that satisfies this is document 1. So it has you or Sam I am, and it doesn't have them. Great. Now, we can also do anywhere or here and not there. Now, again, these, as they roll off the tongue, it's a lot to process all at once, but we do them one at a time, right? And as usual, we'll start with the inside parentheses, right? So, not there. I don't want any documents that contain there. Okay? So the opposite of there is those 4 documents. Great. Now we're going to take that result and AND it with all the documents that have here. So I need here and not there. So here, okay, well, no documents contain that. Uh-oh. That internal clause, here and not there, has wiped out all of our possible results. Because no documents contain the word here and also not the word there. Because if you look carefully, documents 4 and 5 are the only places either of those show up. So our search term has narrowed itself out, has eliminated itself. Whoops. That's fine. That's how search works. Our Boolean condition has not been satisfied. We still have something left, though, so we want that clause, which is nothing, or anywhere. Okay, so anywhere happens once. We can take that. All right, so our result is just document 6. Okay. This has been a little bit down in the weeds, but hey, this is how we get our heads around this stuff. So these are useful ideas. We have gotten into Boolean operations, how we use them to narrow down search results, all this wonderful stuff. But there's a reason that we're not sticking around with term document incidence matrices. And that's because they have some major limitations. So, what might be some problems with these kinds of indexes? You notice there's a lot of entries, right? So the size of your term document incidence matrix is always going to be the number of terms you have times the number of documents you have. And while it is super useful to have our little bit strings that we can just run Boolean operations on to find out, hey, where do the documents live, right? This is not especially scalable. So you have to store the entire matrix. It's almost all of English times number of documents in Library of Congress. That's big. That's a lot of entries. Hundreds of thousands by hundreds of millions, right? So, and if you notice too, most documents don't contain all of the entire list of the English language. They contain a very small subset. So it's not very sparse. It's full of zeros. It's padded out with zeros. So, and it's useful, right? It's useful for these calculations that we've talked about. The rows are these like happy Boolean strings ready to be operated on very quickly. But we need a more succinct and powerful reference structure. And that's where we will get to the inverted index next time. So, to recap, linear search, it has its merits and its uses, but it's also limited. We can't do everything by way of linear search. We touched on some basic ideas of runtime, big O notation, something just to get used to thinking about. You don't have to know all of the ins and outs of exactly how it works. Just get used to the usage of big O notation. And then we also talked about how we can process documents into these incidence matrices and some of their limitations. So next up is the index. We'll go beyond these matrices into what is really the fundamental piece of the course, the index, sometimes also known as the inverted index, but we'll shortcut it. We don't typically use anything but index. It's the most efficient structure, and it's really where we lift off into a place of understanding how search actually functions. And as usual, a final thought to leave you with. Think about the runtime of any particularly tedious task in your everyday life. How might you reduce its runtime, and by how much? All right. Thanks. See you soon.